All right, next let's look at some other examples that we use the symbolic method for to get generating function equations. And we'll look at several of the examples that we considered in the first two lectures and see that meromorphic asymptotics directly gets us to accurate asymptotic estimates of coefficients. So derangements, that's one of our classic problems where we want to know the number of permutations of size n that have no singleton cycles. So that's a familiar combinatorial construction. A derangement is a set of cycles where the length of all the cycles is greater than 1. That immediately translates to this generating function equation, e to the minus z over 1 minus z. That's a meromorphic function. It's the ratio of two analytic functions. So our basic procedure is going to apply. What's the singularity? There's only one. It's z equals 1. It's got a strange structure outside, but as for negative z, it gets large, but the singularity is at z equals 1. So then we can easily compute the residue. The derivative of the denominator is minus 1, which cancels the minus, and the numerator valued at the singularity is just e to the minus 1. So then the meromorphic transfer theorem tells us that the coefficient is this e to the minus 1 over 1, and the exponential growth is 1 to the n. So our asymptotic result is that the coefficient of z to the n, which n factorial coefficient z to the n in that generating function, is asymptotic to n factorial over e. And that comes immediately from the meromorphic transfer theorem. And this one also we can generalize. Well, one thing first to notice is that these estimates are extremely accurate, even for small n. For n equals 5, we're within 0.1. And that's because, in this case, there's the error term is simply to do with the numerics of the function. In other cases, there's singularities, but they're exponentially smaller. So let's look at the class of all permutations with no cycles of length less than or equal to m, where m's a parameter. Again, the combinatorial construction through the symbolic method immediately gives a generating function equation that can be pretty complicated to try to find exact expressions for coefficients in that equation. But the meromorphic transfer theorem immediately gives us the asymptotics just as before. Again, there's a pole at 1, and I'll show since I have m, I don't have any plot. And the residue is the same as before. Evaluating the numerator at 1 is e to the minus hm, 1 plus 1 half plus 1/3 minus e to the minus hm. And the derivative of denominator is minus 1, which cancels the minus, so we get e to the minus hm. And again, exactly the same argument. There's no exponential growth, so it approaches 1 over e h to the m. So whatever m is, you can approximate the number of permutations with no cycles of length less than or equal to m by that simple formula. About 1 over e to the hm of them, of all permutations, have no cycles of length less than or equal to m. And that's a very accurate, going to be a very accurate result. And let's look at the singularities of those. So that's the one that I showed for no cycles of size 1. Here's with no cycles of size 2. Still, there's just one singularity, but the growth of the what goes on outside changes in interesting ways. There's still only one singularity, and it's on the real line, and it's closer to the origin by Pringsheim's theorem. So we know all this from the theorems. In terms of the calculation, the whole growth of this complicated thing is even though it's a fantastic thing, looks like an integrated circuit or something, the whole growth is just determined by the value of that singularity that's closest to the origin. So that's derangements. And again, that's kind of a poster child for analytic combinatorics because it's so easy to get to that asymptotic result. Apply the symbolic method, apply the meromorphic transfer theorem, and you're there. Well, that was the same for strings, and actually that's going to be same for many, many of the combinatorial classes that we've considered. Here's another one that we talked about, surjections. So these are the coupon collector sequences, and so they're words of length m with the property that for some m, each of the first m letters appears at least once. So these are all the ones where for m equals 2, here's the ones for m equals 3, and here's the ones for m equals 4 in this case. So that's surjections, and that's one way to look at it. So how many surjections are there? And we saw the combinatorial construction for surjections. A surjection is just a sequence of sets that are none of which is empty. And that immediately translates to the generating function equation. Set that's not empty is e z minus 1. Sequence is 1 over 1 minus. So that's equal to 1 over 2 minus e to the z. That's a meromorphic function. It's a ratio of two analytic functions. So what we care about is the poles. This one has a lot of poles. Whenever z equals log 2 plus or minus 2 to the 2 pi I, there's going to be a pole. The only one we care about is the one that's on the real line closest to the origin. And we just go ahead and turn the crank and apply the theorem. We compute the residue. So differentiate the bottom, you get minus e to z cancels a minus at log 2 is just 1/2. So the coefficient is going to be 1 over 2 log 2, and the exponential growth is going to be log 2 to the n. 1 over 2 log 2 to the n plus 1. Again, immediately from the construction to the generating function through the transfer theorem to the asymptotic result. Again, these other poles might contribute something to the growth, but it's exponentially small, and these are pretty far away. So this is extremely accurate. Even for 3, it's accurate to 3 decimal places. And we can look at general versions of this, like double surjection. So that's like coupon collector sequences where you want to have 2 of everything. So for some m, each of the first m letters appears at least twice. And again, there's a lot of applications for wanting to study these types of combinatorial objects. In terms of the analytic combinatorics, it's just generalizing the one that we just did. It's a sequence of sets where the sets are all 2 or more. Translates to the generating function, so sets all 2 or more is e to z minus 1. Sequence is 1 over 1 minus that. So we have this generating function for r of z. Again, it's meromorphic, ratio of 2 analytic functions. What we care about is when the denominator is 0. This one's getting to be a little more complicated in terms of the singularities, but the key point is that there's only one on the real line. It's closest to the origin. The others are going to be exponentially small. So we have to do a calculation to find the value where on the real line where e to the z equals z plus 2, and that turns out to be 1.14 in this case. And we go ahead and calculate the residue, which is just the derivative of that evaluated here, and turns out to be just 1 over that plus 1. So again, that little calculation immediately gives the asymptotic growth for a number of double surjections. Bing, bing, bing. No matter how complicated the generating function gets, we go right through it to get to the simple asymptotic result. And this one also generalizes, so that's 1, that's 2. You can see the extra poles are their influence is getting weaker. Well, there's one on the imaginary axis that is getting more. And then that one turns into 2, and these other ones that are out here are very tiny, and then turns into 3. It starts to look a little bit more like what we saw for strings, but still there's only one of those poles on the real line that's closest to the origin, and that's the one whose growth determines completely the asymptotics of the coefficient. And this is a big one for surjections. And these poles, it actually in fact, gets a little bit less accurate. These are, this one is closer than all these other ones. The one on the real line is closer to the origin than all the others. But now they're going to start to contribute possibly to what we see when we do calculations. And it's a little bit like the roots of unity, and then there's going to be, therefore, some oscillations. But all of that is explained by properties of the function in the complex plane. And we can do results as precise as we want, as long as we're willing to do some calculations. All right, here's another one, alignments. So this is sequences of labeled cycles. It's not quite like permutations, which are sets of labeled cycles. So this is sequences where the order matters. It's called alignments. And this is just an example giving the number of alignments for 1, 2, 3, and 4. And by now, pretty much everyone can figure out what's going to happen next. We're going to build a combinatorial construction, sequence of cycles. A cycle is log of 1 over 1 minus. A sequence is 1 over 1 minus that, so there's the generating function for alignments without really much thought at all. That's a meromorphic function. It's a ratio of 2 analytic functions, and so it's when the denominator gets to be 0 that we care about. This one's got one giant singularity where log of 1 over 1 minus z equals 1. And that's exactly when z equals 1 minus 1 over e. You plug that in, then you get a check. That's the dominant singularity. And there's others out there. But then we just do the calculation. Numerator's 1, differentiate that. You get 1 over 1 minus z. Evaluate at 1 over 1 minus e, just get 1 over e again. So that tells us that the exponential growth is 1 over 1 minus e to the n. And the constant is this divided by that, which gives the n plus 1. So that's, again, enumerating the alignments. Combinatorial class maybe we never heard of, but we can immediately get to coefficient asymptotics that's extremely accurate. And this again shows how accurate it is even for small n. And final example that we looked at is set partitions. How many ways are there to partition an n-element set into R subsets? And we talked about this one in lecture 3. And this is the one that the application is rhyming schemes. How many ways are there to rhyme a poem? So you start by putting the first line in set A, and anybody that rhymes with that goes into set A. And the first one that doesn't rhyme goes into set B, and so forth. And so there's a correspondence between partitioning an element set in R subsets and different rhyming schemes. And there's many other applications of this. So how do we do the asymptotics of this one? Well, and we did this combinatorial construction in lecture 3. It's the first times a sequence of them, times the second, times a sequence of both of them, times the third, times a sequence of all 3, and so forth up to R. And that immediately translates to a simple generating function. And again, this is rational, but it's meromorphic. It's the ratio of 2 analytic functions. We're interested in the root that's closest to the origin. What root is that? Well, there's 1, 1/2, and so forth. 1 over R is going to be closest to the origin. This is what it looks like. And actually, the one that's closest to the origin is a little one, but that's the one that matters. And so now we just again go through the procedure. 1 over R is the pole closest to the origin. So that's going to give us the exponential growth, which is going to be R to the n, inverse of that. And the residue is evaluate the numerator at 1 over R and evaluate the derivative of the denominator at 1 over R. There's a little calculation there involving R to the R's that cancel. The result is 1 over R times R factorial. And that immediately gives the asymptotic growth that the number of poems with R rhymes is asymptotic to R to the n over R factorial. So that's 4 familiar classes and generalizations that are immediately handled by meromorphic asymptotics, all showing with analytic combinatorics we can do a construction immediately to a generating function, immediately to asymptotics of the coefficients.